Thank you very much for inviting me to this seminar. This was quite difficult for me to prepare. So we'll see how we go. So I thought of what would be a good plan for this talk. And I think I'd rather talk about the themes or the arcs of this talk. So arc 1, I want to talk about this relationship between something called a Vinberg monoid, affine Springer fibers, right? And multiplicative Higgs bundles and how they kind of all interrelate to each other, multiplicative Higgs bundles. The second arc is that I will talk about the properties, arc 2. I'll actually talk about the properties of multiplicative affine Springer fibers. So I'll say some, I'll define them. I'll talk about some of their properties. And the global analogs of these multiplicative affine Springer fibers are multiplicative Hitchin fibers. So I'll talk about the multiplicative Hitchin system or the Hitchin fibration. And I'll say some nice things about them, or maybe some not very nice things about them. And then the third arc concerns my work, which is developing a parabolic version of these things. So I'll then talk about parabolic version. Okay, so I know this is a math physics seminar, but this is actually going to be more in the realm of algebraic geometry. I will talk about some math physical things like right now. So, okay, any questions? Okay, very good. It's pretty algebraic. It's very Neubauer-Chow, Hitchin fibration themed. So apologies if you were expecting some physics in here. Okay, so let me talk about the origin story. Okay, so let K be an algebraically closed field. Let G be a connected reductive group. Over K. And let X be a smooth algebraic curve over K. And we would, little k. And we would like to consider like a line bundle over X. Oh, I didn't do this properly. Oh, well, I have to move to the next board. Then for some of us that are new to the world of Higgs bundles, or an L-twisted Higgs bundle, let's say E phi on X consists of a principal G bundle, E on X, and a Higgs field, which is a section phi of the adjoint bundle. And this adjoint bundle is twisted by X. So I can write this, where this is my adjoint bundle, and then I twist this by the line bundle L. And that's what makes it L twisted. So in particular, if L is like the canonical bundle, L equals to K of X, this is your usual Higgs bundle that Nigel Hitchens dreamed of. So in his dreams, the stable bundles, okay, so-called stable Higgs bundles, solve Hitchens equations What are these? Well, they're kind of like the Yang-Mills equations, but then you reduce the Yang-Mills equations from dimension 4 to dimension 2, and then you get these Hitchens equations. And this is where some beautiful like gauge theory and non-abelian Hodge theory and so on and so forth. I love Higgs bundles. I'm a Higgs bundles person. Well, okay, cool. But now I kind of want to look at a local parameterization of Higgs bundles, and you can do this through affine Springer fibers. So now let F be the Laurent series ring. Let O be the Taylor series ring. Then as I was only here 2 weeks ago, not last week, so I don't know what happened last week, but Robin talked about the affine Grassmannian. And I'll say a bit more about this. So there is a, oh, true. Yeah, we're in the same place. Okay. C'est la vie. Okay, so it's a functor that takes a K algebra to sets. So it takes a K algebra R to this quotient of loop groups. G of R of T to G of R of polynomial ring. So if you let G be a matrix group, you can think of this as like matrices whose entries are Laurent series divided by matrices whose entries are paraseries. So it's an in scheme, but what we're really saying is that this is representable by an in-projective in scheme. So it's a direct limit. It's a direct limit of schemes that are projective. And to this, what lives inside here, or at least it's, yes.
What do you mean by divide category sets?
What do I mean by taking the quotient in the category of sets?
Yeah.
Yeah.
Set. Oh, I see. Okay.
Thank you. So what lives in here, at least on the level of K points, is an affine Springer fiber. So if you consider a regular semi-simple, the algebra element that is defined over F. So I replace R with little k. Then I have an affine Springer fiber associated to gamma, which is G R G of K dash that. Okay, affine Springer fibers. Now the affine Grassmannian has a nice interpretation as the moduli space of some bundles. And you can actually interpret the affine Springer fiber, how do you say this? And this is an affine Springer fiber via Higgs bundles. So you can think of this as Higgs bundles E phi on the formal disk, let's say spec of O, with a trivialization over the punctured disk. And here, in particular, the trivialization works as follows. So when I restrict E phi to the spec of F, the punctured disk, it would trivialize, so E would trivialize to the trivial G bundle, and phi would trivialize to your parameter, gamma. So in this wonderful work by Neil Bao in 2010, Le Lemma Fundamental, he showed that Hitchin fibers are products of these affine Springer fibers. So there's this beautiful local global relationship. I'll talk more about that later. But this is how affine Springer fibers came into my life. goes through this Higgs bundles thing. And now I want to do something more multiplicative. So consider a generalization. I'm going to consider a generalization of these affine Springer fibers. I should really say what they are. Affine Springer fiber. Consider a generalization as follows. So we know that the affine Grassmannian admits a Cartan decomposition. So what this says is that you can decompose the affine Grassmannian into GO by GO orbits, and these GO by GO orbits are indexed by the dominant co-weights. So this is right. Technically, you're doing this. So these are this is my notation for dominant co-weights. If G was a matrix group, you can think of this as, this is basically a statement about being able to diagonalize any matrix in, you can say G of F. So G of F, G of O. If G is a matrix group, this is basically the statement that says any matrix in G of F can be diagonalized to like T lambda using integral row and column operations. So you're using somewhat undergraduate linear algebra. So this is the Cartan decomposition. And furthermore, we have some closure properties. So if I took the closure of G of O, T lambda G of O, this is an affine Schubert variety, and this is the union of other like affine Schubert cells. So mu is less than lambda G of O T mu G of O. Oh, and mu is a dominant co-weight. Very good. So now consider, so this is what we call multiplicative affine Springer fiber. So let lambda be inside x dot t plus, and let gamma be now a regular semi-simple group element. So when not in a Lie algebra anymore, then multiplicative affine Springer fibers are the following. At least on the level, at least theoretically speaking, they are the following. So now my multiplicative affine Springer fiber depends on two different parameters, a lambda and a gamma, and it takes all G in the affine Grassmannian such that add G inverse gamma lies inside one of these like affine Schubert cells. There's also another version of this, which we will call x less than or equal to lambda or gamma. And basically you can take the closure of this and you can consider another like multiplicative affine Springer fiber. So that's why, yeah, it is plural. Okay, so this one is open inside this one. So this one goes into here as an open subset, at least. And I just want to say a remark that this is not a very unsurprising object, at least in the realm of arithmetic geometry. People have studied these things. So X lambda of gamma in particular is what people would call an affine Deligne-Lustig variety. But without the sigma twisted conjugation. Oh. Sigma twisted conjugation. Where sigma is the the friendly Frobenius endomorphism. So here in the affine linguistic variety, it's the same definition, except your conjugation here is G inverse gamma sigma of G. So it might be interesting to ask, okay, how do they compare? Like, how do the geometry of this compares with the geometry of affine linguistic varieties? And in fact, there are many nice similarities, which I'll get to later. Yeah. Any questions? Yes. These things? They are finite dimensional. They're yes, they are finite dimensional. I would have to do that for the parabolic case. Yes. Right now, we don't need the Grothendieck simultaneous resolution. I'm guessing that's what you are referring to. Yeah, we don't need that for now because we are not dealing with parabolic things. Oh, is there a Poisson structure on these things? That's not been, at least when X, no, wait, that's not been studied. I don't know. I don't know that. Okay. So now the question is, thank you for your question. So now the question is, okay, what kind of Higgs bundles do these fibers parameterize? Do these parameters? And the emphatic answer is multiplicative ones. Do these parameterize? And this is where I will now segue into some physics. Answer multiplicative ones. Okay. So this is the origin story of multiplicative Higgs bundles. So in 2003, Markman Hurtubise, they were the first people to study multiplicative Higgs bundles, but it didn't look in the way that it looks now. So they define what they are. They said that, okay, multiplicative Higgs bundles are pairs E phi consisting of a G bundle, principal G bundle over my curve X. And this time, my Higgs field is not the regular kind of Higgs field, but it is a meromorphic section. So phi lives inside X, but away from some divisor, say D. And it lives in the like big adjoint bundle. Or you can call this the automorphism bundle of E. And okay, here D is a divisor. D equals to an I xi divisor.
Then it was E. Because if G is like E is a G torus, or
Right.
G divided by G.
Yeah, they call it the adjoint bundle. It really should be like all of. It's like all of E. Yeah.
Oh, you multiply by 2 with the joint.
Yes. Yeah. The adjoint bundle. Yeah, I could.
Yeah.
They should improve their notation like this or something. But there is now some, because it's meromorphic, there is now some control of the singularities via dominant co-weights. So here, with singularities, right here. There we go. So at the points of your in the support of the divisor, it is controlled by some dominant co-weights. So here lambda I is a dominant co-weight. So locally speaking, you can describe phi as like, locally, it looks like a matrix that are holomorphic and then T to a lambda and then another matrix. Oh, the ni's. I don't know why they did that. It's not. Yeah, it's not like necessary.
It's defect. Defect's D, maybe you want N, yeah. But it just, what formally speaking, that's what's written as, it just kind of assume a polynomial starting from the bottom.
Right. I'll use this region. But I'll leave this for now. This is somewhat more generalized. Okay. And then after a while, no one really studied them until 2009 and 2015. So 2009, it was Charbonneau, Hurtubise. And then 2015, it was someone called Smith. And they related this definition of multiplicative Higgs bundles to to cancel the periodic, to singular G monopoles. So they showed there is a bijective correspondence between multiplicative Higgs bundles on X and some solutions to a physical equation. So solutions, let's say E of phi on S1 times X, where X is a curve, solutions to what they call the Hermitian Einstein Bogomolny equation. And I apologize if I don't go through this in too much detail. So in particular, these solutions will have singularities. Singularities xi of lambda I direct type. So now we're seeing some physics in here. So I think it's important to note that the multiplicative Higgs bundle is an object over X. But these things, principal Higgs bundle, you have a connection, and you also have a meromorphic section. You also have a meromorphic section of alt of E. These live on S1 times X, like circle times X, right? So to go like one way, at least, you have to restrict E to some fiber over S1. And my meromorphic section here is going to be something that's defined by something called a scattering operator. It's basically the monodromy. It's a monodromy action. And then the other way is quite difficult, actually. Okay. Any questions? I guess I'm talking about this because I don't see it written very much and I feel like we need to say more about this. So let me just finish up this origin story. It's not that we've left multiplicative Higgs bundles alone, it's just that I guess the efforts are sparse. So I believe in I think it was 2018, Elliott and Pestuin started working on this types of multiplicative affine Springer, multiplicative Higgs bundles. And they proved that the moduli space of these bundles, they proved that the moduli space was hypercalar. Except when, well, only when X is like Calabi-Yau or something. It's hypercalar. When X is Calabi-Yau. So in particular, they only showed it, so they only consider X to be C, C star, and the elliptic curve. And furthermore, they showed it was a completely integrable system.
The divisor with lambda i's and so on. So is it like for any choice of those? Or?
Right. Yeah. So yes, indeed, you do have to prescribe like a lambda I in here, I guess. Multiplicative Higgs, but you fix the divisor, you fix your dominant co-weights, and you consider multiplicative Higgs bundles that are defined like that. And then this will give you solutions to the Hermitian-Einstein-Bogomolny equation.
What's the modulus?
Yeah, it's a moduli space of multiplicative Higgs bundles with a fixed divisor and
Fixed divisor.
yes.
And so each of those are.
Yes. So
The current time you haven't been twisting.
no twisting yet. Higgs bundles with fixed divisor. And then
Are they
this moduli space? Oh. Okay, I guess from what I know, they are not smooth. Like the moduli space of multiplicative. Yeah. So what I want to do is I really want to go through this paper and make sure that they're saying the right things. Because what we're going to find out, spoiler alert, that the total stack, like if I will define a moduli space of multiplicative Higgs bundles, but the Higgs bundles defined by Neil, and he shows that this is not smooth. Sorry, one of his students showed that this is not smooth. It admits a local model of singularity. Right. Yeah. Right. Right. Yeah. This is certainly questionable. But okay. What is time?
2:44.
Wow, time is flying.
Sorry, I have a question.
Yes.
Okay, so back to this definition, are you requiring theta or psi compose phi in some sense to be zero, like in the usual? Because on a curve.
Yeah, it's on a curve.
But like L need not be kx, right? Like what if it's like, and like which two of it? Yes, sorry. Yes.
Okay, it's all good. So now this is where the Neil stuff comes in. So in 2011, Frank-O'Neill rephrase multiplicative, like this definition of multiplicative Higgs bundles, but in terms of this Vinberg monoid. Of some Vinberg monoid. And the reason for doing so is, well, they wanted to geometrize like orbital integrals of spherical Hecke functions. They wanted to do some number theoretic things, but they found out that when they did it, when you rephrase it in terms of the Vinberg monoid, it gives you to a more, at least to a more richer structure. In more or less words, it allows you to define the multiplicative Hitchin fibration, etc. So theoretically speaking, this is very good for society. Okay. So this is now, okay, so that's the end of the origin story. I'll now talk about the Vinberg monoid. But also, should I take a break? If it's 2:45, I should be taking a break soon, right? Okay. Yeah, it feels early. I feel like I've moved at a snail's pace. Okay. So the goal is that, well, my goal as a postdoc is that I want to inject this Vinberg monoid back into this picture, ultimately speaking. And I want to rephrase these Hermitian-Einstein-Boltzmann equations in terms of the Vinberg monoid. And that's at least what I'm thinking of as a postdoc. But okay, so let's now get to our basic objects. So this time we are going to consider G to be a semi-simple, simply connected group of rank R. If G is reductive, you can just take the simply connected cover of G of the derived subgroup. So, or take simply connected cover of the derived subgroup. It will work out fine. Let T be a maximal torus, and let Z be the center of G. Then I would like to define the Affine group T times G mod Z. This is G plus, where Z embeds into T times G anti-diagonally. That is to say that when you add Z, like an element little z on T times G on TG, it does Z inverse T, ZG. So you can consider other subgroups, like you can consider B plus, which is T times B mod Z. T plus in particular is T times T mod Z. And Z plus is just T. So now I want to create a monoid whose unit group is G plus. So let alpha I be simple roots. Let omega I be fundamental weights. There are R of these. And you can consider with these fundamental weights, you can consider irreducible representations with highest weight omega I. So irreducible reps. Now you want to extend these so that alpha i's in the row omega i's maps on, like it maps G plus. So extend these to alpha I plus which will go now from G plus to Gn. And you have rho plus, which now goes from G plus to GL of B omega I. And this will go from TG to omega I T rho of omega I G. Now, when you put all these components together, one, you create a locally closed embedding of G plus into R copies of Gm. Times R copies of GLs. And so the Vinberg monoid, what it does is that it takes a look at the image of G plus and you basically want to consider its closure. So VG is the normalization of the closure of G plus in this time A of R. So this is the Vinberg monoid. What we will see later, in case my time management is poor, is that multiplicative Higgs bundles are Higgs bundles that are valued in this Vinberg monoid. Let me talk about one other thing that's inside the Vinberg monoid. So another definition. So there is a smooth open dense subvariety in VG called the non-degenerate locus. This is the inverse image of AR times R copies of endomorphisms, but without zero. And this is a smooth open dense subset or subvariety. Okay, so here, just a remark is that, remark is that if you take a look at V0G, you portion it out by T, this is the wonderful compactification of the adjoint group. So the Vinberg monoid has been studied in the theory of spherical varieties compactifications. Pretty cool. Okay, very good. So let me try and speed things up. So there's essentially two different maps that we care about for this Vinberg monoid. So first of all, the Vinberg monoid emits an abelianization map. That is to say that it maps to its G by G quotient. So G times G acts on G plus by left and right multiplication. That action extends to the Vinberg monoid, and you can just take this quotient. This is called the abelianization, alpha G. It's called abelianization. And using the simple roots, you can show that this is ultimately isomorphic to A to the R. What can I say about the abelianization? Alpha G, it's flat with reduced and irreducible fibers. And in fact, this is sort of like a very defining property of VG. VG is like VG, and it's abelianization is like the universal object among all such monoids that has flat abelianization maps with reduced and irreducible fibers. So this is universal among all monoids M and let's say A of M, monoids with the abelianization. So the Vinberg monoid is not just some ordinary monoid that you can find at a bar. It's a very special universal monoid. Okay, very good. So yeah, I'll give an example of abelianization, but let me finish up here by saying that
It's universal.
is universal among all monoids with the same unit group. No, not the same unit group. Is universal among all monoids whose abelianizations are flat with reduced and irreducible fibers.
Oh, G. Where's the G?
Yeah, so I think the statement is that the semi-simple part of the unit group is G. Yeah, that's a extra little description. Okay, actually no, let's do an example. So if G is SL2, G plus exercise can be shown to be GL2. And then VG is essentially 2x2 matrices. In this case, essentially, so let me actually write this out. This is T A, B, C, D inside A1 times endomorphisms of C2, such that the determinant of the matrix is T. The abelianization map in this case is just the determinant map. So alpha G, wait, hold on, let me just, what's a good way to say this? Yeah, let's do that. So BG to AG, this time this is just A1, and this is just a determinant. So this is very much like the classical Lie algebra case in many ways. Unfortunately, when G is of higher rank, it's much more difficult to describe the Vinberg monoid. This is sort of the nice case where I think where this like coincides with the Lie algebra theory. Okay. Questions about this? Okay. So another thing to note is the inverse image of AR times non-zero endomorphisms.
Oh, and the mouth.
Right. Okay. So another thing.
It's not just no limit points here. It's the for every I.
Yeah. So another thing that's very cool about this abelianization map is that the fibers of this over non-zero elements in the base is G, but the fiber over 0 captures some singular behavior, and this is called the asymptotic monoid. So due to abelianization, one can consider VG, so as a family of groups, VG, AG, as a family of groups, like here, let's say this is G, over 1 and 0, such that over 0 you get something weird. So this is alpha G inverse of 0. So similarly to here, right, if you take a look at determinant 0 matrices, or the fiber over 0 in A1, you're going to get determinant 0 matrices in here. Okay, very good. And then maybe after this, we'll take a break. So I'll say one last thing first. So the point of using the Vinberg monoid is that we have an adjoint quotient. We have a lot of the Lie algebra theory that we need. So let me redraw. I was trying to redraw a triangle, but it wasn't working. Okay, so there exists an adjoint quotient on the Vinberg monoid. G, adjoint of G. So we can call this, let's call this C plus. Usually it's called the extended Steinberg base. There's even a Chevalier isomorphism theorem that says that this is isomorphic to closure of T plus mod W. And using simple roots and fundamental and those like representations, you can show that this is A of 2R. Now this maps down to AG, which, okay, let's remember that this is VG mod G times G. And this is A of R. Such that these maps commute. So when we globalize this, when we talk about the multiplicative Higgs fibration, we're basically going to globalize this, and we now have 3 layers. We have the total stack of multiplicative Higgs bundles. We have its affine base, and then we also have something lying underneath all of that. Okay. Let us take a break here because this is the local picture. Thank you. What is the time? Oh, wow, amazing. Okay, so resume in 3:10. Is that it? Oh, yes, okay. Oh. Press pause.
So the alphas should be like some sort of pitch map or something.
Oh, like this alpha G?
Yeah.
Oh, okay, so the agent vibration is really this chi
Oh.
plus. So, like, this is the thing that globalizes to Higgs bundles. So if you take a look at the mapping stack of this, comma X C plus C T mod W.
Hmm.
This is the hidden vibration.
And like, should the nilpotent cone still correspond to like some kind of CBHS type thing, or because like
Oh,
in
in here?
Yeah, in the classical case, right? If you look at like the nilpotent cone, you should expect that it comes from, or like you get like variation of pod structures. But I mean, setup looks, wildly different here.
Yeah, I mean, it looks different, but it should ultimately be the same. So that's the thing, like, no one has studied these bundles. Like, no one has studied the story.
Ah,
So we don't even know about variations of hot structures or anything.
I see. Okay.
Yeah,
Yeah.
this is very wild new territory.
I see.
I'm doing a bad job.
No, I know. No,
I'm going so slow. Okay.
I don't think so. I mean, you have the full 2 hours. But maybe you should define variations of pod structure as things over in the nilpotent cone. You know?
Yeah, I mean,
Yeah.
that's like my new life purpose now is to like whatever we can do for Higgs bundles, what can we do for this multiplicative thing?
right.
Yeah.
Very cool.
Yeah. Oh, yeah. I will need to look through my notes. Hold on. Sorry. Shouldn't swear into. I just said, oh fuck, underneath my breath. I was like, oh no. Oh, this is bad. This is not good. One is dying. Is it okay?
So we don't know what you prepared, right? So it doesn't matter if you don't get to the end of it.
Yeah.
Oh. I think it's fine.
Okay. Hopefully it seems like a more complete story.
Are you sure? You said that was good.
Yeah.
What do I have left?
I have some questions. Yeah, no, I.
It is also new to me.
Yeah.
Consider finite function. Yeah.
Yeah, what is this? So like, so you're considering like this.
Take G and then multiply with portion of the
Oh, okay. Oh, B, sorry. Yes, yeah, sorry.
So it's the multiplicative version. Also you will drop the expression, right? And then on this gadget, there's a Poisson structure. This was defined by Evans and Blue.
Okay.
And then one of the things that they show is that so, okay, so first of all, this maps to G, right? So we just take
Yeah.
the actual and actual P on P, right? Right. And then
Oh, well,
you take a raw cell inside P, and then take the inverse image
mhm.
in the multiplicative version. That's supposed to be analog of the X upper lambda. Right? Because lambda parameterized G of O or switch analog something like the raw cells.
Ah, well, okay, so first of all, parabolic version. Ah, fine. I think this should technically be more aligned with what this is. Except here now, right, like what does one put here? My claim is that it's this. Claim that supposedly is my PhD thesis. Yeah. Yeah. GUI. Or something.
Right. So at least in the finite case, when you take the inverse image of the raw cells, you get Poisson cell varieties. So the finite analog of your definition here, Poisson cell varieties of the multiplicative property.
Ah, okay.
And I find the vague feeling is that there should be some kind of local systems on its kind of cell varieties that you could do generalized class questions. But then on this affine version, I guess you just take this very standard many triple, right? So G double parentheses T and T inverse G double parentheses T as your sub-algebra as many triple, and that gives you Poisson structure on P double bracket, a double parentheses T, then that should give you a Poisson structure.
That sounds nice. That sounds good. Because like for me, like to come up with this definition, I actually I consider the Grothendieck resolution of the Vinberg monoid, which is very much the same definition. This lies in the Vinberg monoid times V mod B, where G belongs to the Vinberg monoid associated to the Borel subgroup. This will map to BG.
What's the universal property of the Vinberg monoid? It's like
Yeah.
AG initial or terminal?
Yeah, I don't know if it's initial or terminal, but basically what it says is that for any monoid like this, like given another monoid that satisfies all these properties, you can write M as a product of VG times AG. And And like you draw like your little diagram. So this is like A of M with its abelianization. You draw a diagram here, it's A of G. There exists a map. There exists an A, and there exists a terminal.
Oh, I see. Okay, so that's the morphism between those things.
Yeah, this is sign.
And then you have a unique map for
Yeah. So then it's like M times. Oh, shoot. I mean VG. VG. And this is like iso. Yeah. Good question. Alright, so. Should I do in the last 15 minutes? I'm thinking that I prepared too much and I don't know what to do. Like, how do I? Sorry.
Sounds like a common trend. I don't know, like what?
Yeah. Yeah. Dying. Dying. Yeah, I guess tomorrow's talk will actually be better. It will be a better version of this talk. Okay. Oh shoot, isn't it time? Hold on.
Like, he said I was, well, like, my logic was like so.
Oh, hello.
That's what he said.
You know, John?
I'm Jonathan.
Oh,
Marielle's a new postdoc.
Oh, I see. I'm a student of Stanley.
okay. Cool.
I like you're like, oh.
I was like confused, like,
No,
oh, okay. I was like, why am I? Oh, right, I see. That's why.
Stable.
from, but,
Homotopy theory applied now.
Oh, okay.
no, I guess not using homotopy theory, right? Pure algebraic geometry.
Me?
Do you?
No,
No, right, okay.
sorry, I don't know any homotopy theory.
No, I didn't expect it.
I do Higgs bundle stuff, supposedly.
Yeah.
Charlie stuff.
I see.
You're very close, right?
You mean he's like attending the talk and now he's realizing that we're not as close as.
This Wednesday, right?
Hmm?
You're giving a talk this Wednesday.
Also
Yeah.
fairly now.
Also now, I'm wearing a mic.
Like, okay, we aren't that close, but like, it sounds like the whole point of your book is like, you're trying to get to the point where this one.
Yeah.
So.
Okay, no. We'll figure it out.
Why are you getting the geometry and physics? Dude, what is that? It's a fucking geometry.
Thank you. I was like, what do I do? Thank you, James. Yeah, I think Aiden Suda like put us in touch. And I found the shuttle, so thank you. Yeah. Okay, should I continue? Do I have to unpause this or?
Is it twice?
I don't think so. Okay, recording.
Okay, so
Oh, because I didn't know, I didn't touch anything, so that's why.
might be it.
Okay.
Yeah.
Okay, welcome back. Hope everyone had a good tea time. Okay, so let's continue. Okay, so I talked about the history of multiplicative Higgs bundles. I talked about multiplicative affine Springer fibers and the Vinberg monoid. And now one is wondering, okay, how do the Vinberg monoid appear in these multiplicative affine Springer fibers? So let's do that. Vg meets X Vinberg gamma. And then eventually I'll talk about how Vg meets those multiplicative Higgs bundles that appeared in the first part of the talk. Okay, so this is how we do it. So first, consider a dominant co-weight of the adjoint torus. Plus this up here. Then one would like to define the scheme, this affine scheme. V lambda AD of G, given by the following Cartesian diagram. We have Vg times TAD. We have spec of O. And we have AG. This is. So this map here, what it does, it takes G and T and maps it to alpha G and times T. And what this map here does is that it takes T and maps it to T of minus W naught of lambda AD, where W naught is the longest element in the Weyl group. So this is sort of more of a subtle notational thing. You'll find literature where they omit the negative W naught, and then you'll find literature where they include it. But I'll include it in this one. So what I would like to do now is consider sort of arc spaces of these guys. So first of all, if we take a look at AGO modulo TADF, this intersection is the space of non-degenerate arcs of AG. That is to say that these are the arcs that generically map into its unit group TAD. Generically map to TAD. Now this thing has a stratification into TADO orbits. So T W naught, the AD, TADO. Now, if we take the pre-image of these pieces of these cells on the alpha G, we can then consider a stratification of the space of non-degenerate arcs in the Vinberg monoid. We can essentially stratify this by V lambda ADG of O. And I'm going to explain what this is. This is an X of T AD plus, such that so these pieces, V lambda ADG of O, emits a Cartan-like decomposition. So you can decompose this into this time G plus O by G plus O orbits. Right. Now, what are the dominant co-weights for G plus? Well, this time it's going to be a pair, right? Because remember that G plus is T times G mod Z. Right, so now that I will now have like two different co-weights sitting up in here. So this will be, I need more space. Apologies. E to the minus W naught over AD mu G plus L where so this very much looks like the closure of some affine Schubert varieties or affine Schubert cells. And that's sort of key. No, not literally.
Oh, in like set or
Right. If I replace VG in this Cartesian diagram with V0 of G, the non-degenerate locus, I will also have that. I can also do this. Okay, so now so there's a lemma. Let's say, so the person who really formalized all this stuff about the Vinberg monoid and multiplicative Higgs bundles is Jingren Qi, who is a new student in 2017. This was from his PhD thesis. G lies inside V lambda AG of GO, if and only if alpha G of that element belongs to T minus W naught lambda AB. And if I take the adjoint image of G, so I call it G of AD, that will lie inside GAD. Oh, T to the left, maybe. Yes. This intersection takes place in AG of O, or yeah, AG of O. AG stabilization. I forgot to mention here that this is a monoid whose unit group is TAD. So similarly here in this so-called second line, VGO intersects with its unit group G plus of F. Okay, so with this, one can then say that, oh, great. Beautiful, yes. Amazing. So in this case, n is just, let's say, a number, TAD, which in this case is just, oh, sorry, the dominant co-weight of TAD, which is just integers that are positive. We can rebuild this diagram as V and G. This is endomorphisms of C2 times GM. This is A1. This is spec of O. T to T to the N. Right. So V and G consists of matrices with determinant, so matrices in here with determinant T to the N. But Vn O of G, the smooth dense open subset or whatever, like if you replace the zero version of this, you get matrices inside Vn of G that has non-zero reduction. So A is non-zero reduction on T. So basically when I bring T to 0, A shouldn't disappear. Like A will be like an actual element. Okay.
The determinant should be least M or deviation of determinant.
Oh. It should be the valuation, but I don't know why. Like, I don't know how I would explain this using this diagram. Right, this is like, this is the determinant of A times, oh, sorry. So this thing is like A, Z, let's say. And this map does determinant of A times Z. So I'm just using this like Cartesian property to say that, yeah, the determinant should be T to the n, or maybe like at least a scalar multiple. Greater or equal to n.
Small, I mean, greater, small, but means to the determinant should go with form T to the should lie in T to the M times O.
Ah, yeah, I see what you mean. Ah, okay. Okay, so this is not quite right. I don't know.
Slightly confused, but I don't know what is the thing what actually.
It should essentially take a fiber of like the abelianization. I think that's what I want.
Just one part.
Yes,
So it means the determinant is fixed.
yes,
Okay, so just make it right.
yeah, that's kind of what I want. Okay.
The scheme over O.
Yeah, it's an affine scheme over spec of O. What? What makes it not a affine scheme over O? Okay. Amazing. Okay, great. Хорошо. Okay. Let's see. Okay. So I'm trying to get to this endpoint, which is the following. So I now want to relate my multiplicative affine Springer fibers to this V lambda AD of G. So first of all, let kappa of G be the Kottwitz homomorphism. So this maps to I1 of G, which is X star of T. So this is the co-character lattice, mod out the co-root lattice. And then let PG be the normal projection from the co-character lattice to pi 1 of G. Again, lemma by Xi in his thesis is that if kappa of G of gamma is equals to PG of lambda, right, then there exists an element, or one can construct an element, gamma of lambda inside G plus F, such that its image under the abelianization map is exactly T to the minus W naught lambda AD, PAD of O. Here, lambda AD is just the adjoint image of lambda. And when I take the adjoint image of gamma of AD, this is exactly AD. And this is sort of the unifying piece to our puzzle, which is that I can now rewrite my affine Springer my multiplicative affine Springer fibers in the following way. G inside GRG. Oops. Gamma of lambda inside. G. AD. And so now I can finally view these multiplicative affine Springer fibers as, you know, it looks like it now has like an affine Springer fiber description. These parametrized multiplicative Higgs bundles on the formal disk with a trivialization over the punctured disk, and the Higgs field in that case trivializes to gamma of lambda. So I can now endow these with like an in-scheme structure. Okay, very good. Okay, and now let's take a brief, so before I move on to like multiplicative Hitch and stuff, let's kind of go back to those multiplicative Higgs bundles that we talked about earlier. So maybe interlude. VG meets multiplicative Higgs bundles. So I'm taking this from Neil. So how can we see so yeah, let me remind ourselves, like, what is a multiplicative Higgs bundles? So we have what a multiplicative Higgs bundle consists of E phi, where E is a principal G bundle and phi is like H naught. What's on the fixed divisor? E times G. And here, this meromorphic section has, you know, I'm just going to rewrite this. It has prescribed singularities controlled by these dominant co-weights, lambda I inside X star, T plus. Okay, so now consider these representations again. So let rho of omega I be these irreducible representations, irreducible reps of G with highest weight omega I. And now let's go. So phi, my meromorphic section, will induce a section which I will call this, of the endomorphism of this endomorphism, this associated bundle. So I'll give it a name. I'm going to call it end of omega IE. And this is going to be defined as E times G end of B omega I. Here, the action of G on this is induced by rho. So this will occur on yeah, okay. So for all I. So phi is only defined on X on this complement of the divisor. So this will only occur on X support of the divisor. Now, what happens when you go towards the singular points? So over the singular points, this section extends to a section phi of I inside here, tensed by this is where I have to use different oh yeah, okay, hold on a second. J equals to 1. B. So this condition here, when you translate it to this, it gives me this condition here. It tells me how the section will extend over the singularities. Here, okay, let me try and be more. My divisor is given by NJ. So that's what this is doing here. Okay, very good. So basically we can repackage phi. So what Neil and Franco says is that we can repackage phi as well as these phi i's into a single map. A single map. Let's call it like phi tilde that maps into the closure of the following. Pi rho of omega I G inside here. This lies inside this. And when you take the closure, and you're taking this closure in like our copies of the endomorphisms. Now this looks very familiar. This mapping here is exactly rho plus of omega I. So that is how the Vinberg monoid appears again. So what this board is meant to say is that given a multiplicative Higgs bundle, you can it will induce all these maps in all these different sections such that you essentially get you essentially like recover the construction of the Vinberg monoid in some sense. I wish that Neil and Franco wrote this better, but this is all I have. Because it seems very important. It seems so important. Okay. Very good. Time. What is time? Okay. Okay, so given the very little time that I have, let me sort of give you a storyboard of what's going on. Okay. So we had this local story, which is this multiplicative affine Springer fibers. First of all, so maybe just a summary of results, which is one, you can interpret, as I mentioned, you can interpret in terms of multiplicative Higgs bundles. So you can endow this with an in-scheme structure. Two, these guys, X lambda gamma and X less than lambda gamma, are represented by an equidimensional K scheme. Locally of finite type. And for completeness or for wholesomeness, I will give the dimension. Now, unlike the Lie algebra affine Springer fibers, this now will have some dependence on lambda. So you should this is reflected in the dimension formula. Rho lambda plus. So like the dimension formula of affine Springer fibers, it relies on some valuation of the determinant, but it's not the same map. So the algebra one, and then C gamma is the same. So this is the rank of G minus the rank of the centralizer. So it all looks very nice. It looks very much like the Lie algebra theory, but there are some caveats here. So first of all, unfortunately, if you take the regular elements of your affine Springer fiber, this is usually like in the Lie algebra story, this is usually dense in the affine Springer fiber. This time it is not. This is not dense. And X lambda of gamma. Also, this is not like you can consider an action of the local Picard on these guys. This is not a PA torso like the Lie algebra story. Right, so these are elements in VG such that, what was it? The dimension of a centralizer or something is as small as possible or whatever. This is G equals. It's like the Lie algebra definition of like a regular algebra. So like you consider maps that go from X to V reg G, G. Yeah.
It's an open subset, but
Correct.
components.
Yeah. This just broke. This is not a PA torsor. Right, so yes, there are other irreducible components outside of the regular locus. So at least when gamma is split, or so what do I mean by split? It kind of looks like T to the some mu or wait. It lies inside after conjugation. You can essentially view it as lying inside T of O. What is it here? G plus F? Something like this. When gamma is split, Chi did some work on relating the irreducible components of X lambda of gamma to the irreducible components of a Merkovich-Villanen cycle. And he showed that the number of irreducible components is essentially some kind of weight multiplicity. So this is what happens when gamma is split or unramified. You can actually relate the geometry of this to Merkovich-Villanen cycles. This is by Chi 17. It is still an open question as to what to do when gamma is just general elements of gamma. And we don't know if we have this nice thing happening. Okay. Very good. Similarly, we have a global story. Which is that, so you can kind of do it like in the Lie algebra case. where you consider mapping stacks to all of these things. T times T of there's AG of T. Oh, my apologies. This should be C plus. What was AG of T? So you can consider the series of mapping stacks. And there is a map from bun T to bun TAD. Actually, no, we don't have time for this. So one can define a subset in here as the moduli space of multiplicative Higgs bundles. It essentially maps into something here, which is the affine Hitchin brace. And this lies over something in here. So let me write here, multiplicative Hitchin base. And over here is something called the space of boundary divisors. So we have something in this. So this is what we call the multiplicative Hitchin vibration. Everything is more concrete when you twist everything by L. So now let L be a T torsor, or you can take the center of G plus, which is T. And this is a T torsor. So if I add an L to all of these things, if I twist all of my all the monoids I'm working with L, then essentially what I would get is mx of L. So very concretely, this will parameterize E phi, where E is a G bundle, principal G bundle on X. And phi is a Higgs field, but now valued inside a twisted Vinberg monoid. In this case, we can also describe the Hitchin base a bit more concretely. This is just this is a direct sum of R copies of X alpha IL plus R copies of X omega IL. So this is my Hitchin vibration. Now, there's also a piece lying underneath this, as I said. There's a space of boundary divisors, and the space of boundary divisors is simply just the sections of the push forwards of L by the simple roots. Right. Okay. Okay, so that's sort of what's going on in this global story. Let me give a summary of results of what is going on in there. So first of all, we have a product formula, which if those are unfamiliar, it basically says that there is a homeomorphism between Hitchin fibers M of A and modulo some action of the Picard. Let me write this a little bit early. This is the global Picard to some like product of affine Springer fibers. This is not going to go well for me. My notation is failing me here, but essentially, maybe I should just write this in words. Hydrogen fiber. Homeomorphic to multiplicative affine Springer fibers. And it's pretty much the same proof as the algebra case. And this is modulo Picard actions. Actions by Picard stacks. Now, secondly, the total stack, mx, this is not smooth. Oh yeah, sorry. The product formula only occurs over an affine open subset of the base, which is in the so-called anisotropic locus. So this is the same story. This is the anisotropic locus. Okay, back to this. So the total stack here is not smooth. This is a big difference from the Lie algebra case. But what Wang 24 does is that he shows that a smaller open subset, namely this locus over the locus over the generically regular semisimple one, this admits a local model of singularities. What do I mean by this? Okay, so Wang, who was a Nobel Child student who also graduated maybe last year, he constructed this so-called, let me see, how do I do this? So the construction of this local model of singularities. He first constructs something called a global affine Schubert scheme. Qx over the space of boundary divisors. And essentially what the statement says is that you can have an evaluation map from M heart to this local model, modulo some G action. And this takes place over over B. Now, when you restrict this to B, like to each element of B, so for every B in Bx that are very G and ample, one has to define a notion of ampleness for boundary divisors. You can consider the restriction here, part B, to here, O plus G. And this will be formally smooth. This is what we mean by local model of singularities. Now over B, Q of B looks like a product of it looks like a product of affine Schubert cells. So over B, so let's say given boundary divisor B with boundary divisor, let's call it lambda equals to this. Oh, right. You guys don't even know what a boundary divisor is. Apologies. Okay, let me write this in words. Q of B is just a product of affine Schubert cells. This is a statement that says that locally it looks like G mod GR, like some affine Schubert cells, like GR of G. Something like this. Okay, So it's sort of like a summary of what's going on in the global story. Now do I have time? Okay. What is the time? Thank you. Okay. So I know that I sort of messed up the structure of this talk a bit. So 1 hour is the first hour is supposedly expositional and the second hour is supposedly research. But it looks like I have 5 minutes for some research. My apologies. This is why I found it to be a very hard talk to. I was surprised by like how much time I had, and I didn't know if I should try and explain everything, but obviously one shouldn't try to explain everything. So let me talk about some research stuff. Okay. So you have this general, I guess, story about this local story about affine Springer fibers, this global story about multiplicative Higgs systems, and some summary of results. So this question that I want to pose is that what do the parabolic versions of these things look like? What do parabolic versions of x lambda gamma and these multiplicative Higgs vibration? What is the parabolic version of this? And I guess in my thesis, I defined this parabolic version as follows. So now it takes place in the affine flag variety. And here I want to put this. So in the Lie algebra case, you would normally put the Lie subalgebra of like some Borel subalgebra or maybe an Iwahari. But now I want to replace this with some Bruhat cells, some particular Bruhat cells. Right, so just remember that in the affine flag variety, which is GF mod I, you have a Bruhat decomposition that are indexed by I orbits, well, that are indexed by this extended affine vowel group. So here, the extended affine vowel group is defined as co-weight lattice semi-direct product with W. So for example, if G was GL2, no, yes, this would be like Z2, and this would be like S2 for GL2. So similarly, I want to now do a closed version of the one above. So what I'm going to do is I'm going to take the closure of this and this gives me this ultimately gives me the following. So I can rewrite this closure of the union by the so-called admissible union. And I will define what that is. So here, the admissible union of lambda is elements inside the extended affine vowel group such that it is smaller than Tx of lambda, where for some x and w. So if you write this all out, like, okay, the closure of Bruhat cells is just the unions of other Bruhat cells where W is smaller than something, this is what you would get. Okay. So a remark. This one, the lower one, is not, again, it's not a very outlandish object. This is just, it has appeared in arithmetic geometry. This is the admissible union without the sigma twisted conjugation. So it's very cool that if you kind of work through, you kind of work out what the parabolic multiplicative Higgs bundles look like, you actually end up with something that has appeared in, you know, in arithmetic geometry. You end up with this like invisible union. Okay, very good. I guess I will. So let me finish off by saying some other things that I've done besides defining these. So I've also defined, so another thesis thing. I've also defined the parabolic multiplicative Hitchin vibration, which goes from dx x. Very much the same thing as the parabolic Hitchin vibration, which is Xu Yun's work. I've also showed that these things are equidimensional. And the dimension of this is equal to the dimension of the normal multiplicative Affine Springer. And this is very much similar to the algebra case. Okay, I guess I can end it there. So thank you. Any questions? Okay.
The second question that is probably one of the most important parts. So what exactly, I mean, you had a definition of multiplicative fibers, and then you're given kind of an equivalent definition using Vinberg.
Correct.
What exactly did you gain by that? So why is it that maybe I'll ask the other question. Like, so I mean, you have this additive story, you have a multiplicative story. So usually when you have something additive, something multiplicative, you also supposed to have something elliptic. So do you have elliptic Springer?
No, I do not have elliptic affine Springer fibers. I don't know how I would. Yeah, I'm not sure how one would begin to start that story. Right. What do we gain from? Let me go to your first question. So the earlier definition, or the earliest definition of a multiplicative Higgs bundle, with that definition, it's hard to define affine Springer fibers. It's hard to define the multiplicative Hitchin vibration without the Vinberg monoid. And I guess correct, yes. Right. I defined those without any, like, initially I defined those without any Vinberg monoid stuff, but throughout the course of this talk, we showed that the Vinberg monoid does appear inside. Right. Okay, so which other def? So that allows me to view multiplicative affine Springer fibers as those that parameterize multiplicative Higgs bundles. Like before, this one was like G of GRG inside adjoint of gamma inside GO. So at this point, yes, correct.
So you're saying that.
So when they define these other, like the earlier definition of multiplicative Higgs bundles, like when they defined it, they didn't know that it was that you can phrase it in this like in scheme structure way. They didn't study these fibers with those multiplicative Higgs bundles. That makes sense.
Yeah, but even in the additive case, it's not that I don't say about like
Right. Right, and we didn't do this delicate work here. Because ultimately this is like, you can replace this with D lambda AD of G. Right, so there is some delicate work here to say that, okay, if I do this replacement, well, actually, this to me immediately gives you the fact that these parameterized multiplicative Higgs bundles in which the Higgs field is valued in the Vinberg monoid. When you rephrase this to this, then it's sort of like more apparent. Right. That's the question. Like, would I get that definition? Thank you. Any other questions? Yes. Have I computed a cohomology? No. No, I have not. Wang in 24, his name is gone. Wang, he did multiplicative fundamental lemma. And so he had to play with like cohomology, endoscopy groups, etc. So it might be in there. I didn't personally compute it. Okay. Any other questions? Okay. Thank you. Apologies for this very chaotic talk. What's happening? Okay. Oh, that's nice. Okay. Okay. I'm very sorry. Yeah, sorry about this. Yes. Yeah, oh wait, the X gamma lambdas. I think I wrote it down. It's over there.
Oh, there it is.
Yeah. I missed a lot of the details, but it's actually very hard to prove this dimension formula. You need like global methods, like the multiplicative Hitchin fibration to do this. You can't just do it using local results, like the Affine Springer fiber case.
You might have mentioned this already, but is there a map to the first map?
A map for, oh,
Yeah, like somehow the dimension, like for slices in the Affine map.
I'm confused. What?
Or like the dimension of each, like if you take the Affine map, dimension of that, it's like.
Uh-huh. Right.
I just.
I'm a little bit confused because these guys are suddenly, they live inside here. Right? So. Okay. Okay, hold on. So maybe let's just do the Lie algebra case. Right. So in a way to package these into like you want to view them as like fibers, but it's actually like sort of difficult to do this. So he's gone. But that's what he was relating to the Grothendieck simultaneous resolution. Like, so this is GB inside here such that G lies in B. Right. It's kind of hard. You can sort of do this for like normal affine Springer fibers. I guess you have to take GRG times GO or something. Right, if you want to like rephrase it in this definition, but kind of hard. People usually just play with these.